Alright, welcome to another AQA chemistry video, and today we're going to be doing oxidation, or the second part of the video of the oxidation of alcohols. I'm going to be going through the oxidation methods and the practical setup that you need to understand for your exam, or the two really that you really need to know in order to undergo the oxidation to get the specific the specific product that you want, and the reaction products that you'd get and the way to identify them. So we'll start off, we're going to talk about primary alcohol oxidation. And looking further into the oxidation of primary alcohols, you can determine how to produce an aldehyde or a carboxylic acid. So the oxidation of a primary alcohol, as we've seen before, there's like two possible oxidations of the primary alcohols. Depending on the reaction method that you use. One produces an aldehyde, and the other produces a carboxylic acid. So when we're producing an aldehyde, the way we do it is by simple distillation, and you need to be able to draw this in your exam. So first of all, you need to have a heating mantle. You need to have some sort of some way of heating it up. So it could be a water bath, or you can use any form like an electric heating mantle. They may ask you, for example, why would you use an electric heating mantle, or what a heating mantle is, instead of using a straight Bunsen burner? Because a Bunsen burner, remember you have an alcohol here. Alcohols are flammable, so it's better to use alcohols are flammable. So you use a Bunsen burner directly, that can cause your ethanol to combust, and you don't want that, and the pressure in that could cause your apparatus to explode. So you don't really want to do that. So it doesn't need to be a very detailed image, but just to show that just label it as well. That I wouldn't go too much detail. They get what it is. That's a heating. You want to have your flask in here. It'll be a straight neck. That's absolutely terrible. Right, so you have your flask here. It'll be connected to this. It has a neck here. You have your thermometer. That's allowed to pass. It doesn't go all the way down. Make sure to do that. Great. So always remember to label what you have here. So I prefer to just do it at the end actually, but yeah, I already started already. Heating mantle. Yeah, so using a heating mantle would be better because it can equally distribute the heat, so it prevents the superheating that you would get with the Bunsen burner. You'd use a ruler, to be fair, when you're drawing these structures, I guess. I'm just doing it because I'm just getting a rough method, but and I need to have it in here. Oop. So you get into this little, it's actually more like that if I'm being deadly honest, and you have an ice bath. Right. And you need to have, so you have the structure, it's not complete yet actually. You need to have a lipid condenser or a condenser jacket. It would be, yes. And it's actually important that you draw it like the way I've drawn it, the lipid condenser. I'll explain why. You must specify that it's water in coming in from the bottom side here, and it's going up, not going down, and it must have water out coming from the top side. Good to have a tap here actually. Thermometer. This is usually like a 6-mark question or something like that when it asks you to draw this out, and you get a mark for each thing that I think it's usually done by bands. You get a band for each thing that you remember to put in, and it could be between a top band would be obviously 5 and 6 marks. So make sure to have everything, and this would be just calling it a lipid condenser. And then you have your flask, round bottom flask containing I'd say it's containing also you need to have your anti-bumping granules. Is to prevent you'll have anti-bumping granules to prevent bubbling, because if there's bubbling there, basically the anti-bumping granules, they collide against the bubbles to prevent any bubbling from happening, and because bubbling could cause some of your product to leave your reaction vessel, which you don't want to happen, obviously. Yes, it's a round bottom flask containing your primary alcohol, whatever it is that you're using. With potassium dichromate. And obviously there'll be some aldehyde that forms from there. And you have your ice bath and your aldehyde that's been collected. In theory, technically, when you're doing this reaction, you're not going to get a pure sample of aldehyde. So you have to run this experiment many, many times, which is the one downside of having simple distillation, but it's the only way of actually doing it. To make an aldehyde, you carry out the reaction under simple distillation. Let me just make sure I didn't forget anything in case I did. I don't really ever forgot anything. Yeah. Yeah. So to make an aldehyde, you carry out the reaction under simple distillation. And this condenses any reacted aldehyde, which forms as a gas into a new flask. So as I said before, the reason why this works because you have your sample in here, and aldehydes have a lower boiling point compared to ethanol, because it's another way of something that they ask in the exams as well, why ethanol has a higher boiling point than aldehydes, and that's because with ethanol they form hydrogen bonding. I haven't gone through. I don't know if the people watching this has actually gone through it, but it's something that you have either learned or will learn. The different types of bonding. Hydrogen bonding is much stronger than weak van der Waals forces, which are what aldehydes form. And so that's why when you heat it up, and heat is needed to actually allow this oxidation reaction to happen actually, but it's more to do with the fact that once the aldehyde has been formed, since aldehydes have a lower boiling point compared to ethanol, since aldehydes have a lower boiling point compared to alcohols, they will immediately evaporate, and then when you get to the lipid condenser, they'll condense. And the reason why the water has to go through the bottom side here is that you have to have cold water. You have to have cold water rushing up front, because otherwise, if you had water coming in, hot water, if you had cold water coming in from here, it means that there's no temperature gradient, because it'll eventually get to a point where it's hot water here, where so you have cold water in it, but it's still warmer over here, and therefore it wouldn't condense. Whereas if it's cold water coming up here and hot coming up here, so it then forms an equilibrium, and where it's going to be cold enough, it's always going to reach this point where it's going to be very cold, and therefore it's going to condense no matter what. However, if you have it from this side, it won't. It'll eventually get warmer here, and it could evaporate once again. So it has to be coming up from this side, and if you don't do it right like this in the exam, you won't get the mark. Actually, they do specify it has to be like this, and yeah. this is closed from the top here. Tap, I don't think you actually really need to draw that out, but show that a way of collecting it. Now, to produce carboxylic acids, if you have a primary alcohol, to make carboxylic acids, you can carry out the reaction under reflux, and this involves use of a reflux condenser. The reflux condenser condenses any gases and forces them back into the reaction vessel, and this puts aldehydes back in the flask to be oxidized again. So I'm not gonna draw out again because I don't really need to go and draw out. You have to draw this out in the exam, but just to save time, I've just got an image of it, what it is here. It's the same principle, but there's no it doesn't leave, like it's not getting collected back. It's not getting collected. It's with this one here. This condenser jacket is just put on the long neck of the flask, and there's no separate side. There's no side arm where the gases can gas that gets liquefied back again or condensed. It doesn't get collected separately, because what you want is, you have to remember that carboxylic acid is the final form of oxidation of these alcohols, of these primary alcohols. So that means it doesn't need to be collected and done again. Because technically you could do simple distillation on aldehydes, but it means that, as I said before, the risks with, not risks, but downsides of forming of simple distillation is that this is not going to be a pure product. You have to run this reaction over and over again, and even if you do, it's still not a pure sample, or you're less likely to get a pure sample compared to with carboxylic acids. When you with reflux, when you do it, you still have this this the situation here with the watering going in this side from the bottom side and water on the top side, but it's all in the same column. So when this your primary alcohol is being oxidized here, it will go up. The aldehyde will form, and then obviously aldehydes have a low boiling point, so they will evaporate. They will eventually condense in the condenser jacket, and they'll drop back into the reaction vessel, where they will remember there's potassium dichromate in here with it, so it will re-oxidize again. The aldehyde will re-oxidize to the final form, which is the carboxylic acid. So it means that all of your primary alcohol will be condensed into, if it's there for long enough, all of it will oxidize back into into the carboxylic acid that you need. It'll go always to the final form. So this is not a good method for aldehydes because you can't monitor it, you can't stop it. So this is more for forming carboxylic acids to get into that final form. So testing oxidation products, we can determine whether a chemical is either an aldehyde or a ketone through two simple test tube reactions. So with aldehydes and ketones, remember, like, there's, just if I was going to do remembering that an aldehyde I'm drawing this out because aldehydes and ketones are very similar functional groups, which makes it hard to tell apart. So they both share a carbonyl group. They both have this, basically. And when you're doing IR spectra, which you should have, or I guess you will learn, or should have learned, IR spectra, they can be separate. You can determine if you're doing IR spectra, or I think this is only IR spectra really. No, carbon-13 NMR as well. You can determine separately if it's an aldehyde. You can determine separately if it's an aldehyde ketone or aldehyde carbonyl or a ketone carbonyl, but it's sometimes quite hard to tell. And it's better to do a test tube reaction to determine whether or not it's a ketone and it's aldehyde, which is much more clear, much more decisive. But there are instances where you can't do a test tube reaction with carboxylic acids and ketones. You can't do it, but with aldehydes and ketones, there are ways to separate them and determine which one. So the one feature that they have that's different is the oxidizing ability. So oxidizing agents can be used to identify which functional group is present. Oxidizing ability, so oxidizing, if I wanted to go from a aldehyde to a carboxylic acid, this is a reversible reaction, I need to, because OH here. This is a reversible reaction because there are ways to actually reduce your carboxylic acid back into an aldehyde and back into a primary alcohol. But besides that, you don't really need to go through that in this video. So aldehydes can be oxidized further to carboxylic acids just because, as I said before, they have the CH bond, as I said in the previous video. They possess a CH, a carbon-hydrogen bond that can be easily broken down by oxidation. So it's a very weak bond that can be broken, so that allows you to form. It means that it allows you to go and form the OH because you've already formed the carbon OH, the C double bond O. So now you can go and easily form a C OH bond or a carbon to oxygen bond here because you can break the CH bond. And ketones can't do this further because you would have to break the carbon-carbon bond, which is a much stronger 4-electron covalent bond. Point being, is just there's no carbon-hydrogen bonds, and you're not going to break carbon-carbon covalent bonds because they're too strong. Now, Felling's reagent. There's two types of reagents that you can use to identify aldehydes specifically, and to, I guess, discount ketones. I wouldn't really say you're identifying it as a ketone because, well, you'll see. Our first test is with Felling's solution, which is the one I always use in the exam because it's the one I always remember and it's a very easy one. It kind of reminds me of Benedict's reagent in biology, and it contains a Cu2 plus ion, and it's a deep blue, and it's deep blue, and it's also a deep blue solution, I should say. And when you add an aldehyde to Cu2 plus, when you add an aldehyde to the Felling's reagent, it causes the Cu2 plus to oxidize the aldehyde, and it is reduced to Cu plus. So, and when the Cu2 plus is reduced after oxidizing the aldehyde, when it's reduced to a Cu plus, it causes a color change from a deep blue solution to a brick red precipitate. And that's very important. That don't just say it turns brick red, say brick red precipitate. It's important. In fact, they do drop your mark for not saying brick red precipitate because it doesn't form a red brick red solution, it forms a brick red precipitate. Whereas with a ketone, as I said before, it doesn't really prove it. It just shows that it's not an aldehyde, really. If they tell you it's an aldehyde and a ketone, then you can say this is the ketone and this is the aldehyde. But if it just says there's two compounds here and one of them turns Felling's reagent from a blue solution to a brick red precipitate, you know that's an aldehyde. Whereas ketones, there's no color change because it can't be oxidized. As I said before, they can't break carbon-carbon bonds. But that means that if they tell you that there's only an aldehyde and a ketone here, you know that's going to be the ketone because it can't be oxidized. But if they just say it turns a one solution, there's a color change for one solution from blue to brick red aldehyde, but if it doesn't say the same thing for the other one, or there's no color change, that doesn't necessarily mean there's a ketone there. Some people make the confusion, say, oh, if there's no color change, it's a ketone. It just means that it's not an aldehyde. Unless it's specifically specified there's a ketone present, you can't assume that it's, because it could be another compound that's not a ketone either, but it shows the exact same results. Anyway, I'm going to stop talking too much because I need to make this video before 20 minutes. There's tolerance reagent. Tolerance reagent contains a diamine. No, that's not diamine. It's a diamine. Yeah, tolerance reagent contains a diamine silver 1+ ion. You learn about transition metals when you go into year 2, but it's a clear solution, and this reagent oxidizes. So this is the tolerance reagent is the other reagent that you can use, and this reagent oxidizes an aldehyde, but it won't do anything to a ketone, as you already know. When oxidizing an aldehyde, it's reduced to solid silver. So this solution becomes reduced as it oxidizes the aldehyde, and it forms a solid silver, and it's said to be, according to what AQA want you to say, it forms a silver mirror, which it does, to be honest. I could show you an example, but I'm not going to. But what happens is that it forms a silver mirror around the walls of the test tube when it gets reduced. And and that's because it's forming solid silver, and it's actually how they used to make it's how they used to make mirrors back in the day, but they use a different method now. But it makes sure to say it forms a silver mirror. If they ever ask you, it's a very rare that they'll ask you, but if ever ask you why to use Fellings instead of Tollens, is that silver is very expensive. You probably wouldn't have Tollens reagent, a lot of it around, but they probably won't ask that. So for the overall test results for Felling solution, if it's an aldehyde, you'll turn the deep blue in your solution. It will look deep blue because of the Fellings reagent. If an aldehyde is present, there'll be a color change from a deep blue solution to form a brick red precipitate. Oh. Whereas ketones will remains deep blue. There. Whereas Tollens reagent, it goes from clear to a clear solution to form a silver mirror around. I should say a silver mirror around the walls of the test tube. Should run out of space there. And whereas ketone remains clear because it can't be oxidized any further. Right, the oxidation of primary alcohols, to sum it up. So they have the oxidation conditions. It could be done under reflux. And it forces any gas back into the reaction vessel for further oxidation. So this is if you want to form a carboxylic acid. So it forces any gases. Oh, I can't write today. Back into reaction vessel for further oxidation. Guys, just remember, I write these notes so that you don't have to write these notes. You know, these are all here for you. You don't really need to write a lot of notes, just what you need. And that produces, sorry, I've got to say, produces carboxylic acids. I mean, I act like these notes are my notes completely. That's a lie. I'm not gonna lie to you guys. I've taken inspiration, let's just say, from Seneca and Erling. But I tried to teach. I don't know. So under distillation, you have, it condenses desired products into a flask. And when it does so, you form an you produce really an aldehyde. Produce, form, whatever, but produces an aldehyde. And that's it. Hopefully this video helped, and that's it.